Cool.
Okay, so this is the video portion of the presentation on maps, right? So you should have already listened to the audio portion, and you should have at least gotten to this slide, which shows an excerpt of a 1 to 24,000 scale United States Geological Service topographic map, which is the standard map that's used in the United States for field science, right? So, obviously the blue is rivers and lakes, right? These unusually irregular brown lines are contour lines, and contour lines, as I've already discussed, connect places of equal elevation, points with equal elevation. So in theory, if a contour line was actually marked on the ground and you walked along it, you would neither go up nor down. You would stay level, even though you might be walking along parallel to a slope, right? The little black squares and rectangles are buildings. These other lines, like this dashed white and red line, that's a road. That's a larger road. That's the route number. These double black lines are smaller local roads. And these even smaller dashed lines are undeveloped roads that are not perhaps paved. They may be all-weather roads, which have gravel on them but not pavement, like this. You know, this is a partly undeveloped road. You'll notice that the font for natural features is different from that for cultural features. So Lower Village is a place name. Stowe is a place name for these communities, right? You'll notice that it's like a Roman font with serifs. This is italic. Obviously, this refers to a larger thing, like a township or something like that. Tabor Hill, which is a sans serif font, is a natural feature. It's not italic, but it's a different font, right? So things like rivers and lakes typically have a Roman font. These have a sans serif font, like the hills, right? The contour lines are labeled, so that's 1,000 feet, 900 feet, right? So those are major contour lines because they're labeled. And then there are intermediate ones, and you can calculate the contour line interval by looking at the labeled line. So here we have 900, then we have 1, 2, 3, 4, 5 lines to get to 1,000 feet. So the interval, the vertical interval between the contour lines is 20 feet, right? BM means benchmark, and typically that's an elevation, so 670 feet. Little things with like X's are typically point elevations. I don't see a lot here. Now that's a cross, not an X. That's a point elevation, even though I don't see the X. That's a point, oh, there's the X for that point elevation. That's a point elevation. Other cultural resource type things that you should be aware of is that cemeteries are sometimes marked. Typically they're not eligible for the National Register of Historic Places, but they are important cultural resources. You can't just bulldoze them. You know, so we do record them, and you know, state historic preservation offices and other cultural resources type organizations are interested in and concerned about those kinds of things, right? So let's move to a local contour map or a local quadrangle map and inspect it so that you learn what the different parts are and how you use it. Remember, the United States Geological Survey has a number of different map series. Each map series has a characteristic scale so that all the maps are at the same scale and they meet up, you know, the edges match up typically. The most detailed maps that we make on a national level or national scale are the 1 to 24,000 scale map series, which covers the whole country, I think with the exception of Alaska, which is mapped at a different scale because it's in a different part of the globe and it's very large and there's not a lot of cultural stuff going on. Well, I mean, there are not a lot of settlements. So, the 1 to 24,000 map series is also called the 7.5 minute series because of its dimensions in latitude and longitude, right? So, I'm going to take the camera and give you a little tour of the map. So, here is the scale, right? Now, you'll notice that there are several scales, right? There's a metric scale in kilometers, and there is a scale in feet, and there's a scale in miles. But the scale that's important to us is the mathematical scale, which shows the ratio between distances on the map and distances in real life. And that's where it says scale 1:24,000, right? And what that tells you is that if you want to know the size of anything on the ground, you can measure it on the map and then multiply by 24,000, right? So, you know, if you want to know the distance from, you know, here to here, you can measure it with a ruler and then multiply that by 24,000 to know how big it is on the ground, right? So, that's a very important fact that's going to come up again and again as we work with the maps, right? So there's the scale. You can use the sort of the scale bars to measure stuff, but it's not very accurate. It's more accurate to take a careful measurement using a ruler or even calipers and then multiply it by the scale of the map, which is 24,000. Similarly, if you know the size of something on the ground and you want to draw it on the map, you can divide it by 24,000 in whatever units you're using. Remember, the scale is dimensionless, right? It works for feet, inches, cubits, rods, anything you want. It just means that stuff on the ground is 24,000 times bigger than they are on the map, right? Now, here's the north arrow, right? How complicated is that? So you can see that there's one arrow that says MN, right? That's magnetic north. And then there's an arrow in the middle that points to a star, which I believe means celestial north. And then there's one that's GN to the right, and that stands for grid north, right? And the grid on the map is the UTM grid. So that's north in the UTM system, the Universal Transverse Mercator System, which we're going to talk about in our next presentation, right? Now, what else do we have on the map? Well, we have the name and date and edition of the map here in the lower left corner. We also have a little legend that shows, you know, what some of the roads, how some of the roads are marked, right? You know, primary highway surface, hard surface, secondary surface, right? So this particular sheet of the 1 to 24,000 map series, or the 7.5 map series, topographic, right, is named the Fort Lauderdale North, Florida quadrangle, right? The original map is from 1962, as you can see, and it's photo revised in 1983, and the photo revisions are in like purple or maroon. And if you look at the map, you see there's lots of purple and maroon, right? Those represent the 1983 revisions. I don't think the USGS uses that color for photo revisions anymore, but there are a lot of maps around that still have those lines on them, right? You'll notice, I don't know if you can tell, but this is I-95, and it was new then, right? We also have the name of the map sheet up in the upper right. That's typical. Sometimes they're in different corners, but you know, when you're doing technical work and scholarly and scientific work, you need to cite your sources. So if you say, oh, on the map, it shows that there's a cave here, you need to cite the map. Well, this is how you cite the map. You know, you have a name, and below the name you have a serial number for that particular map. And you cite that plus the date of the edition, which in this case would be 1983 photo revision, right? Below that it says DMA, which is Defense Mapping Agency, da 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 da. So that's just another way of describing the map, right? Now, in the lower right corner we have another set of information, and what's important for us, note the fact that it's a polyconic projection. It has a 10,000 foot grid based on Florida Coordinate System East Zone. That is what's called the state plane system, which I will describe briefly in the next presentation. But those numbers that it's referring to there are like this one, right? 660,000 feet, and there's a tick mark, right? And then somewhere along here, there's another one. Actually, I don't see another one. Well, that's the northing. And then somewhere here, we have the easting. See, here we have the 750,000 feet east in the state plane system. And you know it's state plane because it's in feet. Engineers in the United States still use feet. So where it says here, the 10,000 foot grid ticks based on Florida Coordinate System East Zone, it's referring to the state plane coordinate system. As I say, I'll explain what that is, and you need to know what it is, but you don't need to do anything with it. Now, it also says 1,000 meter universal transverse Mercator grid ticks, zone 17, shown in blue. That's these. I can't get my finger to appear. There it is. So this is, you see, that's blue. And this is the label, which actually stands for 2,890,000 meters north, right? So along the east and west edges of the map, right, we have the UTM tick marks for the northings, right? So this is 2,900,000 meters north of the equator, literally is what that means. And then up in the northwest corner, they typically have the full UTM coordinate in meters written out. And you can see it's written out in a funny way, right? It says little 2, little 9, big 03, and little 000, little m, big N. The way you read that basically is 2,903,000 meters north of the equator, right? And then if we just go up here in the northwest corner of the map, here's the easting, right? And what does that say? 576,000 meters east. And again, you can see it's the blue tick mark, which is for the UTM coordinate system. Now, if we go to the next tick mark over, you'll see that it says 577. Well, that actually means 577,000 meters east. But to save space and to simplify the margins of the map, they just drop the last 3 zeros. But this is 576,000, this is 577,000, this is 578,000. They're 1,000 meters apart, which is the same as a kilometer, right? Now, we also have, along the margins of the map, we have latitude and longitude. So you can see that, here we're at, 80 degrees, 15 minutes west longitude and 26 degrees, 15 minutes north latitude. You know, it's good to know what those numbers are, but we don't usually calculate our position or locate our position on topo maps using latitude and longitude because it's complicated and difficult, involves a lot of curves and very complex calculations. Okay? Now, just a few other things. Here in South Florida, the ground is very flat. So there aren't a lot of contour lines, right? But where the hell is the... Here we go. This is a contour line. Like in the illustration in the PowerPoint, it's brown and it has a sans serif font and it's in italics, right? That's the 10-foot contour line. If you were to walk along that line of course does not appear on the ground, right? It's just on the map. But if you were to walk along it, you'd be walking along the ground level along the 10-foot line, right? Here is a point elevation. So where that little X is, it's 9 feet above sea level. Typically, it's, you know, the elevations are referenced against a vertical datum that is mean sea level. Of course, that changes over time, as we all know, right? Now, here's a red thing, right? There's something in red. We haven't seen too much in red. That's a section number, right? So if we zoom out a little bit, you can see here we've got a red line, and I don't know where this red line is missing, but there's a red line. It goes like that. That's a 1 meter square called a section, which is part of the Public Land Survey System, which, again, I will explain in the next presentation, right? Now, one other thing down here. This map, the coordinates on this map are with respect to the 1927 North American datum. That is often abbreviated NAD 27, right? We no longer use that very much. We use the 1983 North American datum. Here, it explains how to adjust, right? So you need to move a line 38 meters south and 23 meters west to get to the new datum that everybody uses. One reason why this is important is that if you're taking points with your GPS, you need to set the GPS to use the same datum as the map if you want to draw the points on the map. Or if you have coordinates from this map and you're trying to navigate to that point, you also need to use the same datum, or you're going to be, well, in some cases, hundreds of meters away. In this case, it's 20, 30, 40 meters. But, you know, in some cases, the datum represents a much more significant change in the location of things. Just so you know, if you're trying to set the datum on your GPS, and maybe it doesn't have an NAD 83, you can use WGS 84, which is World Geodetic System of 1984. But it is important to pay attention to what the datum of the map is. Obviously, new maps use the current datum, but there are still a lot of maps around that have not been updated that are still show coordinates and projections with reference to the 1927 datum, which was in use for many, many years, obviously, right? So that's a little tour of quad maps. We're going to talk about more of these details in the next set of presentations. You know, these are townships for the Public Land Survey System. These are ranges for the Public Land Survey System. You know, as we talked about before, you know, there are different, so this is a municipal boundary. This is a place name. There are many different symbols. And we're going to talk about the different symbols that are available and used on these maps. You need a legend, and I have posted a PDF copy of the United States Geological Survey topographic map symbols online for you to consult and carry around and possibly print out and bring with you in the field. You know, many maps have a complete legend on them, but the legend for these maps is so long and complicated that it's a separate document. And since it applies to every map in the series, of which there are many thousands, it doesn't make sense to print it on every map. So they print basically a pamphlet, and you can carry the pamphlet around with you, and if you need to consult it, you can. In most cases, you know, with a little bit of practice, you'll learn all the symbols that you need to know. But sometimes it's good to have the topographic map legend along with you. And so with that, I'm going to stop this video presentation, and you can go to the next presentation, which is on map projections, in which we, am I framed properly? You do it. So the next presentation is on map projections, and we'll talk about what projections are and how they work, and specifically we'll talk in detail about the universal transverse Mercator projection, which we use very widely in archaeology and other field sciences. We'll also talk a little bit about the public land survey system, which you also need to know in order to do field work. And I'll mention the state plane coordinate system and a few other details. Okay, thanks very much. Take care. Bye-bye.